Swayam Prabha. Digital India. Educated India.
More detail about those numbers we shall be discussing first in this topic, and then we will be gradually moving on to the hydraulic model study. Well, to start with dimensional analysis, what is that? Any physical phenomenon can be expressed in the form of an equation. Well, that equation may contain dimensional and non-dimensional terms. So, after knowing the physical process or a phenomenon, understanding the physical process of a particular phenomenon, we can express that in terms of a equation, and that is why we are using a lot of equations in hydraulic engineering. And those equations will contain some of the terms which will be having dimension. Dimension means we know the very basic fundamentals of dimension already from fluid mechanics concept. So, say density, what is the dimension of that? Mass per unit volume. So, it will be mass divided by volume, and volume, what is the dimension of volume? It is length cubed. So, m by L cube will be the dimension of density. So, that way for some of the term there will be dimension, and it may contain some constant term, and if we combine some of the term, that may become again a non-dimensional term. Like that, a equation will be containing some dimensional and some non-dimensional term. A study of dimension helps in getting engineering solution to many problems. Well, our basic target is to find solution to our problem, and if we do the study of dimension, then it helps us in getting solution to the problem. How? That, of course, when we will be discussing further, it will be more clear. Well, and dimensional analysis helps in, so how it helps? The testing dimensional homogeneity of any equation. So, what we mean by dimensional homogeneity? Say, in a equation we will be having some left hand side and the right hand side, fine. Now, if the left hand side and the right hand side, if we just write the dimension of the left hand side, well, say if it is Q, discharge, then it will be having some dimension, or suppose depth we are talking about. Depth dimension is nothing but L, length dimension, simply depth. So, suppose on the left hand side we have a quantity, this will be having some dimension. Again, on the right hand side we may be having some quantity which will be having some dimension. If the dimension of left hand side and right hand side are matching, then that equation we refer as dimensionally homogeneous equation, or this equation have dimensional homogeneity. Well, and by observing that, how it helps? So, if a equation is having dimensional homogeneity, then we know that yes, it has an analytical basis, and that way we are deriving this. But if it is not having that sort of dimensional homogeneity, that means it might be coming from some observation or empirical things, empirical, that may be one empirical equation. So, that way, say when we talk about Manning's equation, we are not having dimensional homogeneity. So, if we do not know where from that equation is coming, what its origin, whether we can apply this equation directly in some problem, that can be understood more clearly if we check the dimensional homogeneity of that particular equation. say if the equation is not having dimensional homogeneity and it is containing some constant and say exponents, that sort of exponent and constants are there, then we should understand that this equation is developed from some observation, and as such directly we should not rather apply in any other situation if we do not know the original of that particular equation, how it was developed. Well, so the next point, that it helps in deriving equations in terms of non-dimensional parameter. Understanding dimensional analysis, it helps us in deriving non-dimensional equation, because if we recall our class of uniform flow, there also we derived one equation which was non-dimensional equation, and that sort of non-dimensional equation we can derive once we know that what dimension is, what is dimensional analysis. So that way also it helps. Then more importantly, it helps in conducting hydraulic model study. Well, when we will be doing hydraulic model study, particularly physical model we are talking about, then the knowledge of dimensional analysis is very important. And for presenting experimental result in terms of non-dimensional number, so we in that aspect also dimensional analysis help us. So say when we were analyzing hydraulic jam, then we were talking about that if Froude number is less than this, then what the Froude number is? Froude number is a non-dimensional term. So we need to know these non-dimensional terms, and that helps us in experimentation. Well, let us move further. When we talk about dimensional analysis, then first we need to see what are the fundamental quantities. Well, what are the fundamental quantities? When we talk about discharge, velocity or depth, mass, all those things, then we find that all these quantity can be expressed in terms of some fundamental quantities, and those fundamental quantities are, if we see, it is mass. So mass is one quantity which is fundamental. Then length, that is another quantity. Time, then another quantity is temperature. So these four quantities are normally considered as fundamental or primary quantities. Of course, some people prefer to have force in place of mass. Of course, we know that mass, force and mass, there is a relation that force is equal to mass into acceleration. So if we have mass, then acceleration is nothing but length per unit time is velocity, then velocity per unit time, so it will become length by time squared. That become the dimension for acceleration. So once we know the mass dimension, then multiplying that by the length by time square dimension, then we can get the dimension for force. And some people prefer to have the fundamental quantities as force, length, time and temperature as fundamental quantities. Okay, and these are, well, normally we go for this one, but some people prefer this one, and other quantities such as velocity, acceleration, power, whatever it may be, say viscosity, all these coefficient of viscosity, all these quantity are called derived quantity. Okay, so these are called derived quantity or secondary quantities. Well, so that way we should be clear about which part is fundamental, which part is derived, and when we go for dimensional analysis, we express all other quantity, these are which are derived quantity, in terms of the fundamental quantity. Okay, and temperature, that of course I have mentioned here, but the temperature is useful for compressible fluid. If our fluid is compressible, then temperature has significant influence, and in those things, those quantities, the temperature will also be coming. Of course, in hydraulic engineering, normally we do not encounter this temperature very frequently. Okay, we do not encounter this frequently. Well, then dimensional homogeneity, as I have already explained, that analytically derived equations are generally dimensionally homogeneous. Say if we write one equation, very simple equation, suppose say I mean if we take this from a tank, say water is flowing and this way, then suppose this is the head up to this mass, then we want to know what is V, then we write that V is equal to root over 2gh. Okay. That equation, and of course there may be some coefficient in that, there may be some coefficient. I am writing that coefficient is equal to c for actual velocity. Well, normally we write the expression like that. So, where from this is coming? Where from this is coming? Because we know that head at this point is h at this point, that is just on upstream of this pipe. If we check what is the head, total head, it will be h. Z is same along this line. So, we are talking about say 2 point, one is this one, another is this one, this is 1, this is 2. Now, if we equate the head, say energy, so at this point head is equal to h, and there is no velocity at this point, just on upstream. So, velocity head is 0, only the depth head is coming. So, h, and z of course is same. So, here it is h, and then well I am writing it here. So, from this what you can write, it is head, here is h, and this is equal to, what is the head here? Here the pressure head is 0. 0 means actually we are not talking about absolute pressure, we are talking about atmospheric pressure. So, when we say pressure head is 0, we mean that pressure is atmospheric, like that. So, here pressure, as it is open to the atmosphere, so pressure will become 0. So, what is remaining is only velocity. So, head will be say v square by twice c, and z here is of course 0. So, from that we can write that v is equal to root over twice g h. So, that way we can get the expression for velocity, and this relation is a say analytically derived equation. And of course, in reality there will be some contraction, as we were discussing loss and all those things were there in the pipe earlier in our discussion of pipe flow. So, some coefficient will be coming. This can be put as CV also, coefficient of velocity. Okay. Like that we get this expression, and then if we put say dimension of V, then A's and G everything here, then we will find that this equation is dimensionally homogeneous. But now when we say about empirically derived equation are generally non-homogeneous, say we have used the equation several times, like that what is the equation for normal drift, that for deriving the resistance flow formula, rather resistance flow formula we are writing V is equal to 1 by n then r to the power 2 by 3 and s to the power half. So, that equation we have used several times, and similarly Sezis equation also we have discussed several times. But these equations, I mean these particular equations and the Sezis equation as well. So, this equation, if we put the dimension, this is of course a dimensionless term, as we were saying that in a equation there can be terms which are dimensional, which are non-dimensional. Like the slope is one term which is having no dimension, because slope is what? It is the ratio of how much distance it is falling in how much distance, okay, how much depth it is coming down. Elevation, what is the change in elevation in a particular distance. So, that way this is not having any dimension. So, this is a say non-dimensional quantity, this quantity is not having dimension, but the radius, hydraulic radius is having the dimension of depth. Okay. So, then n is a coefficient and v is the velocity, this dimension is L by T. So, this equation if we put the dimension, we will find that this is not a dimensionally homogeneous equation, dimensional homogeneity is not maintained. Well, then next point what we want to discuss is the method of dimensional analysis. How do we do dimensional analysis? Well, there are different methods, of course two popular methods are there which are generally used. One is Rayleigh's method and another is Buckingham pi theorem. First we will be discussing the Rayleigh method. That in Rayleigh method, the functional relationship of the involved variables, functional relationship of the involved variables. What we mean by involved variables? When we talk about a particular phenomenon, then in that phenomenon some parameters are involved. Okay. So, those involved variables we are talking about. So function, they will be having some relationship. So the functional relationship of the involved variables is expressed in the form of a dimensionally homogeneous exponential equation. So we consider the equation to be exponential first. Of course, the exponent what we will be putting, finally we can find that suppose we are putting q is equal to some other parameter which are related, and for all those parameter initially we are putting a exponential term. Then later on through dimensional analysis we will try to see what the value of this exponent, and then we may find that some of the exponents are becoming 1. That is also possible, but initially we put this as a dimensionally homogeneous exponential equation. Fine. For example, let me take this one. For example, that the discharge q flowing through an orifice under constant head depends on the diameter d, then density rho and viscosity mu and gravity, that is acceleration due to gravity g. And this can be written as, so this relation. So we know that through an orifice, suppose we are providing a constant head in a tank, and from bottom of the tank we are having an orifice, and through this we are finding that water is flowing. Well, then this, how much water will be flowing through the orifice, that will depends on the constant head under which it is flowing. Then it will depend on density of the fluid, it will depend on diameter definitely of the orifice, diameter of the orifice, it will depend on acceleration due to gravity. What is the value of that? Then definitely viscosity mu. So if a highly viscous fluid is kept, it will be flowing lower amount of smaller amount of that fluid will be flowing than a fluid of lower viscosity. So all these parameters are influencing. Well, now how we can write that in Rayleigh's method? We are talking about Rayleigh method. Okay. Well, this can be written as, say, q as a function. We know that q now this discharge is function of all those parameters, and this can be written as, say, q is equal to, so this can be, say, c some coefficient, and then we can write as a product of, well, initially we may not write this coefficient, we can just simply say, may not write this exponent, we can simply say that q is a function of mu, rho, d, h and g. I am writing this of course, but we may not write these things initially. Well, then what we can do, that here we can put this thing, that q is equal to c and say mu to the power a into rho to the power b, d to the power c, h to the power d and g to the power e. Well, now this is our relation. Well, now this relation, now if we put the dimension of this relation, say dimension if we put, then what we can write, what is the dimension of q? This is equal to, say, volume per unit time. So we can write L cube by T, volume per unit time. So this is the dimension. Now C is a constant. C is a constant. So what will be the dimension of that? Constant means it doesn't have any dimension rather, and that how we can write? We can write this as in terms of our, say, our fundamental parameters or fundamental quantities are, say, mass, length and time. Temperature is not playing any role here, so we are considering m, l and t. Now C, which is a constant, that we can write, say, m to the power 0. In fact, m is not there, that means then L to the power 0 and T to the power 0. Well, then this is the dimension for that. Then let us see what is the dimension for mu. Well, if we recall the dimensional initial our study in fluid mechanics, then we can just recall it, that mu, the dimension of mu is equal to mass, then m, that means m, L to the power minus 1, T to the power minus 1. Well, I am not going again back to that one which we are supposed to know at this level. So just we can, as a we can remember that, we can just recall that mu is equal to m, L to the power minus 1, T to the power minus 1. Okay. Now just using that, we can write the dimension of this one as Okay, let me write it as say m by L t, m by L t to the power a. This is same as this one. So, this is m by L t to the power a. Then rho, rho is nothing but density. What is density? Density is mass per unit volume. So, we can write this as mass, then volume is L cube. This is the dimension of volume. Then what is d? Dimension of d is nothing but depth, it is nothing, sorry, it is diameter. Diameter is nothing but L. So, L to the power c. What is the dimension of h? H is head. So, its dimension is again length dimension. So, h to the power d. And what is z? Z is nothing but acceleration due to gravity. Whether it is acceleration due to gravity or acceleration due to anything, but it is basically the dimension wise, it is acceleration, dimension of acceleration. So, what we can write for g? Acceleration dimension, as we know that this can be written as length by say time square. This is the dimension of acceleration. So, this to the power e. Well, now if we just try to equate the dimensions whatever we are getting on left hand side and right hand side, say on the basis, first let us equate say from m. If we equate the dimension of m, here we do not have any value of m. That means here we can write that m to the power 0 is there. Suppose if we write even m to the power 0, there is no problem. So, what is the power of, if we just equate the exponent of this m, here it is 0. So, this will imply 0 on this left hand side from m, it is 0. We are writing the exponent. Then on this side what are there? 0 is of course there. Then m to the power 0 into m to the power a, what it will become? 0 plus a, and then it is m to the power b. So, it will be a, m to the power a plus b. On these we do not have m. So, what is that? This is basically we can write that m to the power 0 is equal to m to the power a plus b. Here also we have m, here also we have m. So, if you combine this m to the power a plus b. So, 0 is equal to a plus b. Then if we compare from L if we compare, L here we have 3, and on this side what we have? Here it is L to the power minus a. So, we will be writing minus a. Then here we have minus 3b. L is at lower position, means at denominator means it is minus 3. So, it is minus 3b. So, we can write minus 3b. Then it is plus c plus d, and this will be plus e. So, this is also one relation we are getting. And from t, what we can get? T here is equal to minus 1. So, this minus 1 is equal to, where we have t further, let us search, this is t is equal to minus a. So, this is minus a. Then here we do not have, here again we have minus twice e. So, we have 3 equations. So, by dimensional analysis, from this relation, just from the functional relation we are starting, we are not using any other analytical basis. Just from the functional relation we are starting, and we are arriving at 3 equations. Now, if we can somehow get the value of a, b, c, d and e, then our problem is solved. We are writing the equation, the q is equal to c into these things to the power this things. If we can get the value of a, b, c, d, e, then we can put the value and we can get the equation straight away. Well, but there are definitely problems. What the main problem is that we have how many unknown? 1, a, b, 2, c, d, e, means total 5 unknown. How many equations we have? We have 3 equations. So, from 3 equations we cannot solve for 5 values. Well, and that is why now, but these equations we can play with this equation. This equation can be used to express, if we can express 3 quantity, well, we have 3 equations. So, 2 quantity if we can express in terms of the other quantity, then there will be left, we will be left with 3 variable, 3 unknown, and then we can definitely solve for that. So, what we can do, that from here what it will be, say this implies b is equal to minus a. So, b we can remove. Now, in place of b we can write minus a. Then from this equation what we can write, that say e we can write, e is equal to So, E is equal to, if I take it to this side, well, we can write E is equal to say half minus A by 2, that is twice E equal to say 1 minus A, and that we can write E is equal to 1 by 2 minus A by 2. So, E also we have expressed, B also we have expressed in terms of A. So, two quantity we have expressed. Well, then C also we can express. Now, here also because we have A and these things are there, B is there. So, if we replace these things, if we replace B and E in this form, then what we will be getting, that this will implies, okay, first we have done this, then from here this will implies say E is equal to, we can express B E C we want to express. So, C is equal to, that will become say 5 by 2 minus thrice A by 2 minus D. So, C also we are expressing in terms of A and D. Well, now in this equation, if we put the value of all this quantity, okay, let me write. So, Q, now how we can write, thus say Q is equal to, Q can be written as C, then we can write mu to the power A, okay, A we are maintaining, mu to the power A, then we have rho to the power B, but rho we will write as minus A, because B is equal to minus A, that we know. Then depth, this is diameter, diameter to the power C, C in place of C we will be writing this one, say 5 by 2 minus 3 by 2 A minus D, okay. Then what we are left with, H to the power D, D we are not disturbing, okay, D let it be. Then what else we have, G to the power, well, we have G to the power E. So, E we can replace as half minus A by 2. If anything is left, we have put all the 5 variables here, mu, rho, D, H, G, fine. So, that is we are getting now here how many variables we have, say A, and then here we have D, these are there, and of course A is here. Well, so now Q is being expressed in this term. If we now can separate those quantity which are having only constant power, we can separate those, then the quantity having power A we can separate, then quantity having power D we can separate. Well, now separating those quantity, this equation will take a shape, well, I am writing the final form, just we need to separate those and we need to write it in this form. So, this Q we can write in the form just combining those things and separating those exponent in the having exponent having the same exponent. If we separate, then we can write it in the form that Q is equal to, I am writing the final form, Q can be written as Q is equal to C by say pi by 4 root over 2, then we can write mu by rho D to the power 3 by 2 G to the power half, then to the this is to the power A, that means all A having A exponent we have separated in this side. Then we have say H by D, because H had the exponent D, so H by D, then D minus half, and then pi by 4, then D square root over twice G H we can separate, and those which do not have exponent, that we are bringing in one side, and then we can write like this, root over G H. Okay. Now, from this expression what we can have, that Q we are getting in this form, and well, we are not in a position to find the value of A and D at this point, but we are having two terms. Well, this should be like that. Now, we are having two terms where, sorry, already I have given the bracket here and here separately. Okay. So, we are having two terms, but we cannot get the exact value of this one, but from this expression we know that Q can be written as, so these are some constant, already these are some constant, then this constant we can put again inside, and we can say that Q is this one, say root over twice GH. These are also constants. So, what we can write, say Q is equal to, we can write say A root over twice GH, and then we can write this as a function of other things we can put as a function. So, constant will be there, then it can go as function of say mu by rho d to the power 3 by 2, then g to the power half. Well, then we can have h by d, and then that way we can complete our relation. Okay. So, this pi by, where from this a is coming? A is nothing but pi by 4 d square. That value we are writing as a here. Okay. So, this way a root over twice gh we are keeping here, q is equal to, and other things which we do not know because the power are there, a and d. So, exponent are there rather. So, we are writing it in this form, and then this equation in fact is the equation for discharge, q is equal to a root over twice gh. We started with one say dimensional equation at the beginning, that v is equal to root over twice gh through orifice, and then if we multiply it by the area, we are getting that this is equal to a root over twice ch. So, as such, this equation can be now written as q is equal to all these things, this function. Now, this function we can write in terms of a coefficient say c d, and then we can have c d a root over twice g h. Fine. So, the equation what we could write earlier, well, here we were writing in fact this equation, that v is equal to c v root over twice gh, or we can write v is equal to, this means if we multiply it by a and v. So, q, this will become q is equal to, then the discharge, suppose I am writing as coefficient of discharge root over twice gh. So, the same equation q is equal to c d root over twice gh, the same equation we are getting here. But what is the advantage of getting this equation? Because at this point when we were getting this equation in this form, then we were just knowing that discharge will not be equal to the exactly calculated value of root over twice gh. There will be some loss and all those things, and because of that there will be some reduction, and that is why the coefficient of discharge is coming, and that coefficient of discharge will be having some numerical value that we can determine experimentally, like say it will be coming 0.68 or something like that. Well, in different for orifice it may be different, for wear it may be different. So, like that coefficient of the charge will be having different value for say different object. But we were not in a position to say that this CD will depends on what, that was not known. But now when we do dimensional analysis, and then we are getting that Q is, yes, this is a CD into A root over twice this. Then we can say that CD value will depends on these parameters, because CD is, we are writing that CD is nothing but function of this one. So, density, viscosity, then diameter, then acceleration due to gravity, what is the head under which it is flowing, those parameters are influencing the value of CD. So, that is the beauty of dimensional analysis. We are in a better position to say that what are the factors that will be influencing the value of CD. Of course, we can determine the exact value experimentally. Well, that way this is what we have explained briefly, the Rayleigh's method. Then if we go for Buckingham pi theorem, let us just discuss that point. If in a physical phenomenon there are n dimensional variables, that means n dimensional variables means we have already discussed what is dimensional, what is non-dimensional variable. But suppose in a particular phenomenon we have n dimensional variables and m fundamental variables or fundamental quantities, say m, l, t, these are fundamental quantities, and in that phenomenon involved fundamental quantities are suppose 3 means m, l, t. Say sometimes if we consider temperature there may be 4, well, and there are suppose n dimensional variables, then the relationship among them can be expressed in terms of n minus m independent dimensionless terms. So that is what the Buckingham pi theorem, and that's why those independent dimensionless term are referred here as pi. What we have actually explained by this one, that if there are say 6 variables involved in that entire phenomenon, and then suppose 3 dimensionless 3 fundamental quantities like this, and then we will be having 3 independent dimensionless term, because m minus n is say 6, n minus m is 6 minus 3, n is equal to 6, m is equal to 3. So that is what we are referring. Well, we will be going further details into that. For example, if p1, p2, p3 up to pn, say n number are the parameters, and there are, of course, we should mention here these are the dimensional parameters or parameters having dimension, and there are m fundamental quantities, then the relation, say our actual relation is, say it is a function of, this can be related as a function of all the parameters, and that can be equate to a constant c, because we know that these parameters are involved in that phenomenon. Of course, we can write say p1 is equal to, we can write this in this form also, p1 is equal to a function of all these, that way also it can be written, or if we just do alteration, then we can write it in this form. So this can be expressed in the form of, say rather than writing this, we can have a different function f2, and this will be say pi 1, pi 2, pi 3, and how many pi or how many dimensionless quantity will be there? It will not be n, it will be n minus m. So up to n minus 1 say dimensionless parameter we can have, and that is equal to say c1, a different constant may be coming. Well, now this Buckingham pi theorem, in it to form the n minus m number of pi term, what we do that m numbers of variable are chosen as repeating variable. Well, we are saying that we will be getting n minus m number of non-dimensional term, but how we will group them? How we will be grouping this non-dimensional term? Because if a particular dimensional term is there, definitely that will be dimensional. To have a non-dimensional term, we will have to group them in a combination that we get a non-dimensional term. So two quantity having different dimension, 2, 3 quantity if we club, and then this entire quantity may form a non-dimensional term. Now how to form that? So we have to tell n number, and how to form that? Well, m numbers of variable are chosen as repeating variable. Some variable will be repeating in all this pi term, and each of remaining m minus n variables are combined with these m variables to form m minus n number of pi terms. Well, that means if we have 6 parameters or 6 dimensional variable, then to form the non-dimensional, or sorry, to form the dimensionless pi term, what we will be doing? We will have to select 3 variable, because we know that our dimensional primary numbers are primary or fundamental quantities are m, l, t, 3. Then so our pi term will be 3, 6 minus 3, it will be 3. So what we will be doing? Out of the 6 variable, 3 variable we will be choosing as repeating variable. That means in each of the pi term, these 3 variable will be there. Then along with this 3 variable, the other remaining 3 variable we will be putting 1 by 1. In one pi term we will be putting remaining variable. Remaining variable are basically n minus m remaining variable. So we are putting 1 from that. Then we are getting 1 pi term. Another in another. So that way we are getting, say, first pi 1, then pi 2, then pi 3 we will be getting by adding the third variable, which is not within repeating variable. Then how many that sort of variables were there which are not in the repeating variable? That will be, say, n minus m. So how many pi term we are forming? That is also n minus m, and that way we form the n minus n number of pi term. Well, now the question is that out of 6 variables, I am just giving an example, the 6 variable, there may be even 10 variable. Then out of the 10 variables, we need to take some variable or suppose if our m, l, t are the fundamental quantities, then we need to take 3 variables as repeating variable. Now, which 3 variables we will be taking as repeating variable? That is the important point. So, these 3 variables we should select in a way that these 3 variables will involve all the m, l, t. Not necessarily that out of these 3, one will have to, each will have to keep m, l, t. It is not like that. But if we see all 3 together, they will have to have m, l, t, all the dimensional parameter, all the dimension they will have to have, all fundamental quantities they will have to have, that is m, l, t. This is one requirement. Well, let us see what the requirement is, and another requirement is that, well, first requirement what we have stated, that the repeating m variables are chosen in a way that they contain among them all the m fundamental dimensions, among them, not individually. Among these 3, all the fundamental dimensions will have to be there. And second point, that they do not form a dimensionless number. See, if these 3 variables, they, if we combine and form a non-dimensional number or dimensionless number, then it will be a problem. It will not serve our purpose. So, these 3 should not form a dimensionless number. Well, that way, this is the criteria of selecting these repeating variable. Well, I will be giving one example quickly. That is, suppose let us consider the same problem what we have discussed, that Q is a function of, discharge is a function of flow through orifice, again we are talking about. So, Q is a function of d, h, g, mu and rho. So, as a function, as we can write, this is a function of all this parameter, and that is equal to C. Well, this we can now write, say, like that, dot, okay, this product. And what it indicates, that number of variables are 6 and fundamental dimensions are 3, that is m, l, t. We do not have, temperature parameter here, so this is a m, l, t. Well, now we are sure that 6 minus 3, this is equal to 3, pi term will be there, and that is why this equation let us write as f2, a different function we are writing, and pi 1, pi 2, pi 3 is equal to c. So, that way we can write the function. And then pi 1, again when we are writing like this with a different constant, we can write that pi 1 is equal to, that this pi can be related to other function also. If we just take it on that side, then we will be having a different function, but we can write pi 1 is equal to c2 into f3 into pi 2 pi 3. So, this way we can write the expression. Now, which repeating variable we will be choosing? Okay, we are knowing fundamentally that this should be. So, considering rho, g and d as repeating variable, 3 terms can be written as. So, how these 3 terms we are getting pi 1, pi 2, pi 3. If we consider rho, g and d as repeating variable, we can write pi 1 is equal to rho to the power a1, d to the power b1, g to the power c1. Well, then we are adding rho, d and g are our repeating variable, and q, mu and h are non-repeating variable. Well, so with the first one we are putting q, the charge, and then pi 2, again this is a2 like that, rho to the power a, so all are exponent, then this mu we are adding here. Then pi 3, this should be pi 3, sorry, this should be pi 3 is equal to rho, d, g, then h we are adding here. Well, now what we can do from this particular expression, we can move further. Of course, time will not permit me to go for the detailed analysis, but just like what we did in case of the Rayleigh method, similarly from this pi is a constant term. So, what will be the dimension? We are saying that pi is a non-dimensional term. So, what will be its dimension? If I write in terms of m, l, t, it will be m to the power 0, l to the power 0, t to the power 0, and we know the dimension of these terms. So, we can again proceed in the way that we did in case of Rayleigh method. Well, briefly I am doing it. Say writing for pi 1, what we can do, say for pi 1 first, I will write for 1 first. So, pi 1 what we can write, say m to the power 0, l to the power 0, then t to the power 0, this is equal to Well, this discharge is the first term here, so we can write that m by L cube to the power say well, this is not we are not writing discharge, but this first term is not q, it is rho. So rho means m by L cube to the power say a1, then d is the length dimension length to the power say b1, g is the length by time square, so this length by time square to the power say c1, and then q, as we know, this is equal to say volume, that is L cube by time, L cube by time. So we are writing like this. Then again, just like that earlier we do here, if we equate m value, that m will give us one equation, L will give us one equation, and T will give us one equation. So from this equation what we can get, say for m we will be getting 0 is equal to a1, because in other times a is not there, and then L will give us a relation that 0 is equal to minus thrice a1 plus b1 plus c1 plus 3, and then T, this will give us one relation 0, because here all are 0 basically, 0 is equal to minus twice c1 minus 1. And from this equation, now here this is a little more easier, because we see we have 3 equation, and from this 3 equation we need to solve for a, b and c. That means 3 quantity we need to solve from 3 equation, which is quite possible, easy. So we can get from here that a is equal to 0, b is equal to a1 is equal to 0, b1 is equal to minus 5 by 2, and c1 is equal to minus half. Well, so that way we can get. So what is our pi term? Now pi 1 we can write, say from that just by putting this expression, because pi already we are expressing. So putting rho to the power a1 means it is 0, so rho is vanishing from that. Q is there, so we are putting q, and then g to the power, what we are getting, c is minus half, so g will be coming g to the power half here, and then d to the power minus 5 by 2, so d will be coming here, d to the power 5 by 2. So our pi 1 is this one. Similarly, going by pi 2 and pi 3, we can have expression for this pi 2 and pi 3 also. Let us just write what is pi 2 and pi 3. We are not doing in detail, but pi 2 we will be getting in the form that it will be containing mu. So it is mu by rho g to the power half, then it is d to the power 3 by 2. Now this remain as exercise. Well, we can always try and we can see whether we are getting this or not. Similarly, pi 3, let us take this also as our exercise. After the class we will be, I mean you can do that. So pi 3, if we just put it like that, then it will become h by d. So that way we are getting, see, h by d, obviously this is non-dimensional term, dimensionless term rather we can say, and this is pi 2 is also a dimensionless term. If we check the dimension of this one, we will be finding that it is a dimensionless term, because we are starting with this principle that these are dimensionless terms. So we are getting this thing. So what our expression can be, now putting this value we can write that f2 pi 1 pi 2 pi 3, this is a function, is equal to c1. So by substituting the above value, what we can write, pi 2, that we can write as q by g to the power half d to the power 5 by 2, and say mu by rho g to the power half d to the power 3 by 2, then we can write h by d. Whatever dimensional term we are getting, that we are dimensionless term what we are getting, that we are putting here, and that we can write that this is equal to say constant c1. Well, this can be written in the form again that q by g to the power half d to the power 5 by 2 is equal to c2, and f we can write mu by rho g to the power half d to the power 3 by 2, then h by t. So this way we are getting a relationship which showing us that q we are expressing in this form. Of course, this relation appears to be different from what relation we obtained earlier, but this we can again change, and then we can write it in a different form, and we can have it in the original form also, which is very familiar form. But so this way we can express the equation for Q. Well, this expression here, this we have already in the earlier method also, Rayleigh's method also we got this one, this also we are getting fine. And then this expression is little different, because earlier we were getting said Q is equal to root over say A into root over twice GH. So that we are obtaining. Well, velocity is equal to, I mean, root over twice GH, so area into velocity we are getting it. Now whether this, if we can write Q is equal to taking this part to that side, we can have it in this form. Now let us just verify whether this term and this term is identical or not. What is the dimension of this term? We can see that it is g to the power half. Okay, root g is here, here also root g is here. So let us keep it. Then here we have root 2, which is a constant. We are not bothering about that. That can be taken to other side. Well, then d to the power 5 means we can have dimension of L, and that is to the power 5 by 2. And now here we can, what we are left with, A and H. Well, so A can have A, the dimension of A we know that pi by 4 d square, and H to the power half, so it is again H to the power half. So what is the dimension of this? If we combine, say it is a constant part, so this d square means we can write L square, and this H has the dimension of L, so L to the power half. If we just combine, this become L to the power, say 2 into 2, so it is 4 plus 1 5, so 5 by 2. So from here also we are getting L to the power 5 by 2, here also we are getting L to the power 5 by 2, this, and then root over g is there here. And so that way dimensionally these quantity are same, dimensionally these quantity are same, and these are otherwise also same. Well, that way we can have some more understanding of a particular phenomenon through dimensional analysis. Well, then some important dimensionless numbers are there. We know about those numbers a little bit already, but we need to do more on that, and that will be required in our hydraulic model study. Well, the force ratio, if we take ratio of two forces, then definitely there will not be any dimension. Both are having dimension of force, so there will not be any dimension. So let us see what is the expression for inertia force. We can write quickly, say inertia force is equal to mass into acceleration. Well, mass into acceleration. So that we can write, say rho density into, say, volume into, say, acceleration. Well, and that we can write in the form that rho into volume into acceleration is nothing but v by t. This v is velocity, so velocity by 2, and that we can write as rho into volume by, say, time into velocity. What is volume by time? Volume per unit time is nothing but the discharge. So we can write rho q into v, or this can be written as rho a into v square. Well, so this dimensionally how we can write these things, this dimension of this one we can write, that is rho, and dimension of, say, a we can write L square and v square. Well, that way also we can write this. Now we will, with using this expression, we are keeping rho and v fine, and this area we are writing in terms of L square from the length dimension. Well, now let us see how we can use this to have a different force ratio. First we will be talking about the ratio inertia viscous force ratio. Okay. Now what is the viscous force expression? Say Fv we can write as, at any point, suppose shear stress is this one, then so viscous shear is this one tau, and then if we multiply this by A, then we are getting, say, viscous force. Okay. So this viscous force we can write, what is tau? We can write mu into dv dy, then we are having area. So this can be written as mu, then this dv dy dimensionally, or say value wise you can write this is b, and then dy is the length dimension, so L, and this area is equal to L square. So we can write this in the form of mu v into L. And just we should remember one point, this length dimension we are writing as, say, not exactly as L, suppose area we are writing as in dimension, that L square. That is why these are called characteristic length, it is representing that way. And then what is the ratio? if we write say Fi by Fv, Fi means this one rho L square V square, and then this we are writing. So, this is equal to rho L square V square divided by mu V L, then this will give us one interesting number what we are using in our all our earlier classes, that is rho then V then L divided by mu, and we know very well what this number is. Well, so this number we call as Reynolds number, okay. Well, then similarly let us see what is the, if we talk about inertia gravity force ratio. So, gravity force, what can be the expression for gravity force? Well, the expression for gravity force we can write that mass into acceleration due to gravity. Again, whether it is due to gravity as acceleration it can be written, but if we are interested to keep the g term here, then how we can write mass is nothing but rho into volume, and then it is g. Now, what is the dimension of volume? So, basically here what we are trying, say the quantity which can be expressed in terms of length dimension, that was a geometrical quantity we are expressing, say rho into volume means we are writing say rho, this volume can be written as L cube, and then we are putting g. So, what is we can now again write Fi by Fg, which is the dimensionless quantity. So, that will be again rho L square V square, that is the inertia force, expression for inertia force, and then we are putting rho L cube into g. So, this will give us another interesting quantity which we are using all in our previous classes, this is V square that will remain, and this will become g, and this is L. Again, that is why we call this L as characteristic length, and for different situations this characteristic length, particularly in Reynolds number, we remember that when we were discussing pipe flow our length was diameter. When we were discussing say open channel flow, this length dimension we took as hydraulic depth. So, that way for different quantity, again when we study boundary layer, then that Reynolds number again we take the length dimension as different. So, that is why it is thus dimensionally we are writing this thing. So, this is V square by ZL, and then of course, this we do not use as a number, this of course is a dimensionless number, but what we do, square root of this, say square root of this number of this, that is V by root over GL, this is called a Froude number, this is called Froude number, okay. These two number we are already getting, but we are just trying to analyze how these are coming. Then some number, Euler number, Newton's number, that will be coming from inertia and pressure force. Well, so what is pressure force? Say Fp, if we write, this is equal to pressure into area, it is very simple, pressure into area. So, pressure we will keep P, and then area we can write L square. So, what will be say Fi by Fp, that will be rho L square V square divided by say P pressure into L square, fine. Well, so that will give us say this expression as V square divided by P, this P, and rho will be coming L square getting cancelled. So, P by rho. Well, and this square root of this is called Euler number again. So, square root of this one of this number is called Euler number, that is V by root over P by rho. This is called Euler number. Well, then again there is another number that is called Newton number, just reciprocal of this one. So, reciprocal of this one, reciprocal say root over P by rho divided by V, this is called Newton number, this is called Newton number. That these are some important dimensionless number that we use many a time in our hydraulic analysis. Another is say inertia elastic ratio, okay, inertia versus elastic force. So, what is the expression for, and that is Cauchy number and Mach number, that is also very important in fluid mechanics particularly. So, say Fe, what is the elastic force, that we can write say bulk modulus of elasticity, fine, that is bulk modulus of elasticity into area. Well, strain is a non-dimensional as bulk modulus, stress by strain. So, stress is the pressure and area it will be force, and strain is of course a non-dimensional term. So, this is Fe we can write in this form, and that is equal to K is normally used as bulk modulus of elasticity. So, this is K into A or KL square. So, this ratio again Fi by Fe, that if we write we will be getting it in the form of V square by K by rho. I am not writing details of this one, just few more steps will be required, and this number is called Cauchy number. Well, and then say this number, if we take square root of this number, this is called say Mach number. So, Mach number, what is that? We can write Mach number is equal to V by root over K by rho. V by root over K by rho. Well, then one more number is popular, that is for surface tension, say Fs. Suppose S represents surface tension, then what we can write? We know that sigma, suppose surface tension value means surface tension force per unit length. So, what will be the force? It will be this multiplied by L. Then again if I take this ratio Fi by Fs, this will be say rho L square V square divided by sigma L. So, that we can write as rho L V square divided by sigma. So, this can be written as V square by sigma by rho L. Well, and then square root of this, again square root of this is equal to say V by root over sigma by rho L, and this number is known as Weber number. This number is known as Weber number. Okay. So, this Weber number. Well, so that way we can have different dimensionless number, and for hydraulic model study these numbers are very important. Well, how these are important and how this help us in developing hydraulic model, that we will be discussing in our next class. Well, thank you very much.